Welcome to the 12th session, and here we begin by answering the question that we raised in the previous session, namely, if I have a continuous function, at least a region in which the function is continuous, can I construct it by using small pulse? So, let me now go back to the answer. So, I have here this function which is smooth, continuous in that region which I have identified, and I have this very narrow pulse spanning an interval of delta and with a height of 1 by delta. You could visualize this pulse moving along the time axis. This function is a function of t, whatever t might be, time for example. And I move that pulse to bring it to a specific location. I brought it to this location here. Let's call it t equal to t0. So, if this pulse were originally at 0 here, and if I give this pulse a name, I call it deltas, capital delta t. So, this is the name I give to this pulse. Then this pulse which I have drawn here can be written as delta capital delta t minus t0, shifted to lie at t0 instead of at 0. And the original function that I have here is x of t as a function of t. Now, I multiply these two and let us see what I get. Multiply them and integrate. Integrate on all time. So, what I am saying is take xt delta capital delta t minus t0, integrate with respect to t for all t, all over the time axis. What do I get? Now, here you need to do a little bit of thinking. So, visualize that you actually have this pulse lying at t0 as it were, and essentially this capital delta is small enough so that the function xt here is almost a constant on that interval. And therefore, all that happens when you multiply xt by delta delta t minus t0 is to capture or to pick that particular value of xt. Maybe you could think of the value at the center, it does not matter. So, in other words, what I am saying formally in mathematical languages, formally xt times delta delta t minus t0 is almost equivalent to x of t0 delta t minus t0. Now, you must appreciate what I am saying here. The two sides of the equation here, I am talking about this equation here, xt into delta t minus t0 is equal to or is equivalent to x of t0 times delta delta t minus t0. The two sides of the equation have a very different meaning. Here you have a product of two functions, and here you have a multiple of the pulse. So, what we are saying is, in the region where the function is continuous, the product of xt with that narrow pulse is just a multiple of that narrow pulse. And now, when I integrate it with respect to all time, I simply get that factor by which it is multiplied coming out, because the pulse has unit area. Now, you understand why we took unit area in the first place. So, let us say it formally. What we are saying is integral x t times delta delta t minus t0 dt over all t is the same as integral minus infinity to plus infinity x of t0 times delta delta t minus t0 dt, but x of t0 is a constant. So, it can come out of the integral. and therefore you have that becoming equal to x of t0 times minus to plus infinity delta delta t minus t0 dt, and this is essentially the area in the pulse, which we can conveniently make 1 or unity. Now, what it means is the pulse, this is one way to understand it. The pulse is like a sieve, or it has a sifting property. In fact, that's the term used formally. The sifting property, as they call it. What does that property say? It says x of t delta delta t minus t0 dt sifts out or pulls out x of t0. Now, we could understand it in a slightly different way. We've also written an intermediate step there. Let us write it again. We wrote down x of t delta delta t minus t0 is equivalent to x of t0 delta delta t minus t0. And then we said that when we integrate xt delta delta t minus t0 dt, we get x of t0. Now, let us take this particular pulse that we drew. Let us assume that it is symmetric about t equal to 0, the original pulse. Let us call it delta delta t. And let us note that delta delta t is equal to delta delta minus t, if we assume that it is centered at 0, as we have done here. Let us use this property to write down a slightly modified equation. The slightly modified equation is integral xt delta delta t minus t0 dt is the same as xt delta delta t0 minus t dt, and this becomes equal to x of t0. Now, this equation has a totally different interpretation. It's beautiful how by twiggling the equations a little bit we come up with new interpretations. We'll see the interpretation in the next session.